Now that we understand how to interpret a linear combination of vectors with specified weights, it's worth taking some time to understand some simple examples of geometric objects that can arise as a set of linear combinations. So in R2, we know that a line is uniquely determined by 2 points, x0, y0, and x1, y1, that lie on the line. So you can always write down the equation of the line using point-slope form. But from the standpoint of vectors, this is somewhat unsatisfying. So we can make it more vector-friendly by remembering that the slope, m, which is y0 minus y1 over x0 minus x1, gives us a direction for the line. And if we have that data plus an extra point through which the line must pass, then the line is also uniquely determined. So we can think about the slope or the direction as a vector by remembering that if you walk 1 unit along the x direction, then the point on the line is m units along the y direction. So we can capture the slope as the direction vector v equals 1m. Now, it's important to note that this vector v does point in the direction, but might not necessarily point along the line. Namely, this vector v we're thinking of as originating from the point 0, 0 and pointing to the point 1m. So at best, it's actually only parallel to our line. So we say that this vector is parallel to the line y minus y0 is equal to m times x minus x0. As a convenient remark, we note that because scaling does not change the direction of the vector, we could also use x1 minus x0 times v, which is going to give us the vector whose coordinates are x1 minus x0 and y1 minus y0 as a vector parallel to the line through y minus y0 is equal to m times x minus x0. So as an example, let's find a vector parallel to the line through the points 4, 5, and 8, 8. We get the slope 3/4. So we can write down the vector v equals 1 3/4. Or, as we observed above, it's sometimes simpler, especially when we have a fraction, to write this as 4, 3. Both vectors point in the same direction. One is simply longer than the other, and the vector with coordinates 4 and 3 is a little simpler to write down than one that has a fraction as a coordinate. So once we have a direction, we can form a line by allowing our scalars to vary. Every point on the line with slope m through the origin has the form x in the x-coordinate and mx in the y-coordinate. So by identifying the point with a vector, we have the following vector equation. This tells us that we can think of all of the points on the line with slope m through the origin as being obtained by scaling the vector v by the number x. So as a set, the line through the origin with slope m is just the set of all pairs x, mx. So we can identify that set with the set of scalar multiples of v, which we write as x times v, such that x is a real number. So we can visualize this in the plane as thinking about the vector v lying on the line with slope m through the origin, and we can think about all the points along that line as being obtained as the tip of a scaled copy of v. So now that we can specify a line with slope m through the origin, we can think about creating a line with slope m through a given point, x0, y0. The simplest way to do this is to translate the line by the vector pointing at our point x0, y0. If we think about how we defined vector addition, then we can do this translation geometrically just by drawing a parallelogram. We can see on the right-hand side of our parallelogram that if we allow v to be scaled and added to w, we'll get the parallel line y minus y naught is equal to m times x minus x naught. As a set of points, we can write the line y minus y naught equals m times x minus x naught as, while as a set of vectors, we can write it as the set w plus x times v, where x is a real number. As an example, we'll express the line through 4, 5, and 8, 8 as a set of vectors. We've already computed a vector with integer entries, which is parallel to this line that we want. That's the vector with entries 4 and 3, which we'll call v. Using the point 4, 5, which we can think of as the vector w with entries 4 and 5, we get a translation vector. So as a set of vectors, our line is just w plus t times v, where t can be any real number that we like. So to generalize to higher dimensions, all we need is a vector that gives a direction and a vector that will give us a point through which the line should pass. So the line through the point w1, w2 down to wm, which lies in Rm, in the direction of a vector v with entries v1 through vm, is specified by the set of all vectors w plus t times v, where t is any real number. Sometimes it's also quite helpful to be able to specify a line using multiple equations. So we observe that if we rewrite that expression w plus tv as a single vector, then we label our coordinate directions in Rm as x1 through xm. Then we can specify the same line using m parametric equations. x1 equals w plus tv1. x2 is w2 plus tv2, down to xm is wm plus tvm. So as an example, let's look at our previous line in R2. Our parametric equations, if we read across the top row, the first one is specifying the x-coordinate. So x is equal to 4 plus 4t. And reading across the bottom, our y-coordinate is given by 5 plus 3t. These are our two parametric equations. They are called parametric because our x-coordinate and our y-coordinate are determined by some parameter t. If we solve the first equation for t, we get t is equal to x minus 4 divided by 4, or you can think of that as 1/4 x minus 1. Now if we plug that back into our expression for y, we'll come up with our familiar form of a line. So we get y is equal to 3/4 x plus 2, which is the usual slope-intercept form from a basic algebra class.